Welcome back to Train Signal Citrix XenApp training. You're watching the Understanding Citrix XenApp Architecture lesson. If you want to learn or master any type of technology in the world or anything at all, one of the building blocks of your educational foundation should be understanding how it works, how the architecture of something works, how it's put together. When you understand the architecture of how things work, you feel like you're inside it. You see the packet moving. You understand how it's moving from point A to point B. But more importantly, when you understand the architecture of something, when it breaks, you know where to look. You can understand and visualize where the problem might be, and therefore you can zoom in on a particular area instead of just sitting in front of your computer screen, typing away and not knowing where to look. So it is very important for your Citrix education, for your XenApp education in general, to understand the architecture that makes up XenApp in general and Citrix's flagship product or remote desktop computing architecture protocol in particular. So what we're going to do in this lesson is we're going to laser focus on the independent computing architecture, the ICA protocol. We're going to dig deep inside of the ICA packet. So we're going to break down the ICA packet so you know how it's constructed, what it's made up of, how the packets are traveling from, through the OSI layer, so on and so forth. We're going to talk about the ICA virtual channels, what they are, how many of them, what are they used for. So we're going to break it down to those minute details. Then we're going to talk about the independent management architecture, or the IMA. What is its role within the Citrix architecture in general, and XenApp in particular. We're going to talk about the different architectural components that make up XenApp, how everything is tied together, what do you need, so on and so forth. I want to highlight zones and their importance, so we're going to talk about that. We're going to talk about the different ports that you need to open or be aware of, whether you're taking the CCA exam or you're trying to troubleshoot something, or you're giving a remote connectivity from outside the network, from inside the network. Which ports does the XenApp environment require so that you understand how to build it, how you communicate with your network team and your security teams. And then finally, we're going to talk about the different XenApp plugins that are available for which operating system, etc., etc. So in order to understand XenApp, in order to understand Citrix in general, you have to understand the importance of the independent computing architecture, the ICA protocol. Today, the ICA protocol is one of the thinnest, best products or remote desktop protocols that you can use because it works very well on the LAN, works very well on the WAN, and it works extremely well over the internet or over any type of a remote connection. I still remember the days when we used to use ICA over a modem, dial up. So the ICA protocol is a very thin protocol that was created to work off of both high latency links and low latency links over the WAN, over the LAN. So it's customized for these types of scenarios. The ICA protocol is a presentation layer protocol on the OSI model. And I mentioned this because, first of all, you need to know it for the exam. It might come up or it might not come up. But the other reason we're going to mention this, we're going to take a look at the OSI layer. Again, we're going to break down the architectural components down to the OSI layer so you can understand how the packets are flowing, thereby getting a better understanding of how ICA works. Again, in the most basic of terms, the ICA protocol is does screen updates, keyboard and mouse clicks. So that's what makes it so thin. Now, obviously, that's not enough when you're doing any kind of a computing environment. You need printing, you need video, you need graphics, so on and so forth. So we'll talk about how the ICA protocol is enhanced to take advantage of these different features and functionality. Again, over the WAN, it's very optimized for the WAN, so it's very, very latency tolerant, works over standard SSL with great performance, so you don't need to open any specific ports for ICA to work. You don't have to do anything in particular. ICA will work very well over just standard SSL that's available on the market today. So again, that doves back into what we talked about in the earlier lesson about seamless integration. This is one example of how it seamlessly integrates with the existing architecture, the existing infrastructure that you have in place. The ICA protocol, you can bandwidth optimize it. So you can put QoS on it. You can say, look, if you're sending printing packets through the ICA protocol, I want you to only give them 10% of the bandwidth. I don't want printing to consume my whole bandwidth that's available. So you can configure and tweak the bandwidth of what is using what basically within the ICA protocol so that the user experience doesn't suffer. So this is kind of funny because this is networking essentials, right? But it all goes back to the OSI model. Everything that we do goes back to the OSI model. So where does the ICA protocol live? Come on, I just said it. Come on, anyone? Right, it's on the presentation layer of the ICA protocol. So again, when you're taking a look at what the ICA model does, or what it shows you, is the user is initiating commands at the application layer. These applications, this data is going to travel through the application layer to the presentation layer, so on and so forth, all the way to the physical medium. Now, once this packet has all this extra frames that are added on top of it, all these encapsulations from the different layers, it gets to the medium, it travels through the medium, and then it starts to sort of go through the reverse process. So it decrypts itself, gives the physical layer whatever its equivalent is sending, so that stays here, then goes up, gives the data link layer the equivalent of what the initiator is sending, leaves that there, and keeps moving all the way up until you get the response on the screen. Now, because the ICA protocol is a presentation layer protocol here, we're going to take a look in the next slide as far as what are the enhancements, what is the ICA protocol doing from a compression, from a reliability standpoint, in order to make the user experience seamless and make it look better and perform much, much better. So let's take a look at the ICA packet. Now, you'll notice here that I have two drawings. You have the ICA packet, which is wrapped into the TCP packet, because this is the transport, right? So ICA is a TCP protocol. It uses the TCP protocol to transport its data. So this is what the packet would look like once it is encapsulated within the TCP packet, for those of you that want to know. But if you want to drill deeper within the ICA packet, you take a look down here, and you'll notice that the ICA packet is made up of different frames. You have the frame head, and we're going to talk about what that means. You have the reliability that the ICA protocol can add to its packets, encapsulation, it can also add this to its packet, compression, and command. Now you'll notice I have command in bold and I have a star next to it, because out of all of these components, command is the only packet that is always required. It always has to be there in order for the ICA packet to exist. So command is the only one of all of those that always has to be there. Now you also have the command data, and you have the frame trailer. So this is what constitutes the ICA packets. All other frames are optional with the exception of the command. So what do these mean? So again, I've listed them all here, and I've put the command in blue. This is important because you need to know that the command is the only packet that exists. So what is the frame head? The frame head is an optional framing protocol header. It's a prefix for framing stream-oriented transport protocol data. So any transport protocol data that you want to add to ICA that is stream-oriented, you would add a frame head. But again, that's an optional frame that you add. If you wanted to add a reliability frame from a transmission protocol perspective, the ICA packet will add the reliable frame to its packet, encrypt that, add it, and then send it down. Encryption, if you're trying to use encryption within the ICA protocol, then the encryption protocol header would have to be added to the ICA packet in order to provide the encryption necessary for that particular packet. Compression, if the ICA packet, if you've enabled compression at the ICA packet level, then again, you will need an optional compression protocol header. That's what takes care of, manages the compression of a particular ICA protocol. Again, the command, as we said earlier, command is required. It's the beginning of the base ICA protocol data, so that always has to exist. Then you have the command data. The command data could be made up of the different virtual channels that we're going to talk about in a second. So that is the bulk, that's the essence of what's going to be transported with the ICA. Now, obviously, it's optional because you got to put something in there in order to transmit it. Then you have the frame trail. That's an optional framing protocol trail. It's the suffix, so it's the completion of the frame head, if I can call it, for any frame asynchronous transport protocol data. So this is what constitutes the ICA packet. This is what the ICA packet is going to put together when it's sending its data, its stuff, through the different layers of the OSI model from point A to point B. I needed to explain to you guys what all of the different optional frames are and the required frames are, so that you understand what makes up that particular ICA packet. Now let's take a look. Now the ICA protocol will encapsulate data into virtual channels. So instead of if you get like audio, for example, you get a packet for audio and you send it across the link. You get a packet for video, you send it across the link. You get a packet for printing, you send it across the link. That is not a very optimized, not very efficient way of transmitting data. So what the ICA protocol does is it creates virtual channels within the particular ICA packet, encapsulate the different types of data, and sends them in one packet. So let's go back to the earlier slide here. So you'll notice within the command data, you'll have all the different virtual channels that you can encapsulate, and then you're putting it inside of a TCP packet and you're sending the whole thing across the wire. So all of the command data will go part of the ICA packet for a better, more efficient way of sending or transmitting data to the other side, to point B, for example. Now, within the ICA protocol, you can have a maximum of 32 virtual channels per session. And keep in mind, one thing is very important here. The RDP virtual channels, because RDP, Microsoft protocol that's equivalent to ICA, also has a set of virtual channels, but they are different than what the ICA channels are. Now, what I've listed here is just a sample of the types of ICA virtual channels that are available that can be encapsulated within the ICA packet and sent over the wire. The most important one you'll notice is the ThinWire 3. This makes up the essence, the architecture of the ICA protocol. It's going to send the video, the keyboard, the mouse clicks, so on and so forth. This is ThinWire. This is at the heart of the ICA packet. You can send printing data, audio, drive mappings, clipboard mappings, seamless windows, so on and so forth. You got up to 32 virtual channels that you can encapsulate. All right, so we talked about the OSI layer. We talked about how things get from point A to point B. But once you have that ICA packet, let's again take a look at how it's connecting the client to the server. So every one of the virtual channels that you have here, and you can have up to 32, will equate to their counterpart at the, so the client is transmitting to the server. If you're sending the graphics, they're going to go through the different layers of the OSI, the different whatever. They're going to go from point A to point B. It's going to be decrypted, and it's going to connect the user or the client session to the server's equivalent on the virtual channel, and that's how the data is going to be exchanged between the client and the server. So the virtual channels are open, obviously, by the application. Applications like, okay, well, I want to send printer. I want to send a printing file over to the server for rendering, and then I want it to be able to print. So you're going to open a virtual channel. It's going to transmit that data within the printer virtual channel. The printer virtual channel is going to encapsulate that within the ICA WinStation driver. It's going to go down to the protocol driver, transmit driver, all of that's going to put all of that in a packet and transmit it to the other side and decrypt it all the way up. So this gives you an idea of how the server or the client is transmitting data to the server and how efficient the ICA protocol is and what it's doing within that packet to compress, to encrypt, to make sure there's a reliability mechanism within the ICA protocol in order to get your packets from point A to point B reliably, safely, obviously, but also with the most efficient way in order to maximize the user experience. Independent Management Architecture, otherwise known as the IMA. It provides a centralized framework for server-to-server communication, and what that means is the IMA is going to be installed on every XenApp server by default, and it allows these servers to communicate between one another, to share information like load, share information of whether a server is still up or not. So it's an architecture by which you control all the XenApp servers, and all the XenApp servers are interconnected between one another. That is the protocol that is used to create the farm, to interconnect the different XenApp servers. So by definition, the IMA is a centralized management facility constructed on a collection of core subsystems that the different XenApp servers can use in order to interconnect. IMA is also the way by which you communicate between your management console and the XenApp server. So when you're sending commands from your management console, you're sending those commands via the independent management architecture to the different XenApp servers. Now, the different XenApp servers will communicate via messages to one another over TCP port 2512, and you'll be able to manage the different XenApp servers from your management console over TCP 2513. And in a slide later on, I will talk about the different ports that are available. But this is what the independent management architecture brings to the table. It is not like the ICA. The ICA is used as a transport or a presentation protocol that enhances those packets. IMA is strictly for management purposes, for Citrix XenApp server to server communication, and for you to be able to issue commands to your XenApp servers from your management console. So it's very different than the ICA protocol. I know that there's only a letter difference technically in the abbreviation, but they are not the same. So make sure you understand the difference. So what are the different XenApp architectural components? Now keep in mind, in a later slide, I'm going to have a slide called the XenApp components. These are the architectural components that make up XenApp. We're going to talk about farms. What is a farm? A farm is a collection of XenApp servers that are grouped together in a logical entity so that you can manage them, deploy resources to them, take resources from them, connect users to them. It's a logical grouping of XenApp servers and resources. You have your XenApp, or you have your different Citrix servers. Servers can be XenApp servers, and the XenApp servers can be application servers, or they can be data collectors. A XenApp application server means it's just a worker server. Kind of think of it as a worker server. All its purpose in life is to service applications to users, published or so on and so forth. A data collector is an elevated XenApp server. It's still a XenApp server, but its role and its function within the farm is different. In larger farms, where there's a lot of XenApp servers, in the hundreds, you would have a XenApp server play the role of a data collector, but doesn't accept any kind of user connections. So all it does is the data collector manages load among other things. So if a user connection request comes in, it's going to go to the data collector. The data collector is going to determine which XenApp server is the least busy and make that connection to the user. So typically, data collectors aren't used to service users, but in smaller farms, 20, 30 servers, 50 servers even, the data collector can be just a normal XenApp server that also services applications. The reason why you separate and isolate it is because if there's a lot of user requests, the CPU will go, will spike up, the different resources for the data collector will spike up, and it might not be very efficient in connecting users to application servers, so they split that role separately. But that's usually in very large environments. So this is the main difference between a data collector and an application server, and we're going to talk a little more about data collectors when we talk about zones a little later on. Then you have the web interface, the secure gateway, and the netscaler. The web interface is a way for users to connect to a portal, log in, authenticate, and launch applications from there. Secure gateway is the equivalent of the web interface, but it's sort of like a bridge between the outside and the inside. So secure gateway is typically deployed in a DMZ. Users are connecting from outside the network, connect to the secure gateway. The secure gateway can have the web interface on the same server, or it can have a web interface on the inside network that it interfaces with and sends that request over SSL and then makes a connection to the server. The netscaler is a more hardened appliance that's not running the Windows operating system. It's literally an appliance that comes in the form of a physical appliance or a virtual appliance that you also deploy in the DMZ, and that becomes sort of like your proxy server to the web interface and to your XenApp farm. Then you have the license server, which, as the name implies, is going to manage all the necessary or needed licenses for this environment. Provisioning services is interesting because it allows you to have, instead of installing XenApp on 10 servers and managing 10 instances of XenApp, you can have a single virtual disk that streams to diskless XenApp servers. So what happens is when the XenApp server boots, it doesn't have a physical or virtual disk local to it. It has a remote virtual disk that it treats as if it was local, but you're booting off of a remote virtual disk. The advantage there is instead of patching and upgrading and installing applications 10 times, you do it once, and the provisioning server will allow you to manage hundreds of XenApp instances from the same virtual disk. So it makes management significantly streamlined. Licensing is another architectural component. We talked about the license server, but I also wanted to stress the fact that licensing is very important in a XenApp architecture because you have the RDS licenses, which are the Microsoft licenses for terminal server and Windows and so on, and you have the Citrix licenses. In the next lesson, we focus on licensing, but I wanted to list that here. Data collectors, again, we listed the data collectors at the server level, but the data collector is one of the architectural components that you should be aware of in a XenApp environment. Then you have the data store, local host cache. The data store is the database that is available on a remote server that all of the XenApp servers connect to for configuration information. Now, the local host cache is typically an access database that is available on every one of the XenApp servers that holds a portion of the main data store database. And the reason for the local host cache is if the XenApp servers lose connectivity with the database server, the data store, they can continue to function off of the locally available minimized version of the database, which is local to them. So the local host cache provides that functionality and bridges the gap between the outage of the XenApp to the data store and until you bring back your database server. So it always has that local host cache, that local database that it can reference that has a subset of the database on the data store. You have hosted applications and you have streamed applications. We talked about that a little bit in the introduction lesson. The hosted applications are applications that you install on a terminal server, on a XenApp server, and then you give, it's like a published application. And streamed applications are packaged applications that you can deliver to your users that run on their endpoint operating system without being installed. The difference between streamed applications and hosted applications, a hosted application will consume the resources of the server that it's being hosted on, whereas the streamed application is packaged and delivered to the endpoint device and it's consuming the resources of that particular endpoint device like CPU and memory and disk and so on and so forth. You have worker groups, which are very interesting. Typically within XenApp farms, the way we've been doing it for years, and we can't seem to break that cycle, is we silo servers. So we'll take servers, we have 100 servers in the farm, and we'll take servers 1 through 5, and we silo them based on the application that is installed on them. So if we have an application that requires 5 servers, we dedicate a number of servers to that application because we want to be able to manage that silo of servers independently. If we want to bring them down to update the application, patch the application, whatever, we don't want to affect the other users that are using other applications. So worker groups allow you to take a collection of XenApp servers, group them together, and manage them as a single entity. You can even take it one step further to say anytime you add a server in Active Directory to a particular OU, that OU, the worker group will basically read that OU and add that server automatically to that particular worker group. That streamlines and speeds up the way you publish applications to a number of servers. You can filter policies, so on and so forth. So worker groups are a way of grouping or siloing servers that are serving the same type. Zones, on the other hand, is a way to geographically group XenApp servers. So if you had XenApp servers in Chicago and you have XenApp servers in London or XenApp servers in California, for example, you would create different zones and thereby think of zones as the equivalent of subnets but for XenApp servers. The XenApp servers within a particular zone can communicate with one another in a more efficient manner. Because the IMA protocol communicates with every XenApp server that it can find within a particular zone, if you had the XenApp servers in London and the XenApp servers in Chicago all in one zone, then you're going to have IMA communicating over that WAN link to all the XenApp servers that are available. Instead, you localize it. So every time you have XenApp servers in a particular geographical location, you create a zone. That way you confine and you contain the IMA traffic to that particular zone. And if zones need to communicate with one another, then the data collector in that zone will communicate with the data collector in the other zone. We're going to focus on that, and I'm going to show you a drawing in the next couple of slides here. But from a XenApp architectural standpoint, I wanted to show you how things are connected. So if you'll notice that you have a client device that's trying to connect from outside the network, goes through the cloud, goes through the internet, whatever you want to call it, goes through the firewall, NetScaler, access gateway, secure gateway, this is in the DMZ, talks to your web interface server, and then you have the zone here. The zone has one data collector. It talks to the data collector. Hey, data collector, which is your least busy server for my particular application? And it connects the user to that particular application. You'll notice we're grouping servers within the zone inside of worker groups based on their application type. So this is a worker group with a bunch of XenApp servers. And then obviously all the XenApp servers will have to communicate with their license server and their database server. And if you're connecting over the LAN or the WAN, you don't go through the DMZ, you go directly to the web interface. So this is in a very simplistic, very basic way of looking at the XenApp architecture and how the different components fit together and interact with one another. Now we talked about zones. It's very important that you keep zone traffic local to that zone. So if you have a zone, again, like we said in Chicago, you want all the XenApp servers to be able to communicate with one another in a very efficient way. So they're all communicating inside the zone, kind of like a subnet. And anytime there needs to be inter-zone connectivity, inter-zone communication, then that zone communication happens between the two data collector, thereby limiting the amount of traffic, limiting the amount of broadcast that is going between site A and site B. Now, any XenApp server within the zone can become a data collector. The data collector isn't, you don't install anything special, you don't install anything. An election happens and one of the XenApp servers is just chosen to be a data collector, unless you specify, again, like I said earlier, in certain environments, because there's a lot of XenApp servers, they elect to have a data collector that serves the function of data collector, does nothing else. So you have the ability, and we'll talk about that when we talk about administration, of specifying and forcing one of the XenApp servers to always be the data collector. Now again, you can force it if you want it to be a data collector and not have any users connect to it, thereby you don't install applications, you don't assign it to any applications, and it serves the function of a data collector. In the event that your primary data collector fails, for whatever reason, hardware issue, software issue, one of the other XenApp servers in the farm picks up. So one of the other servers becomes a data collector. Data collector going down will not affect user connectivity. It won't affect users that are connected or logged in. So it's very seamless transition if a data collector should go offline. All right, now here are the different ports, the different things that you need to know from a ports perspective if you're communicating with your networking team, or even if you're trying to troubleshoot certain things. So the main port to know is obviously port 1494, which is your ICA port. The new port is port TCP 2598, which is ICA with session reliability. Session reliability is a Microsoft sort of a technology that was created that ICA can leverage and take advantage of some of the enhancements that session reliability offers or gives you. Session reliability will do things like, let's say you're working on a session on a train, and the train is going through a tunnel, and that tunnel is all of a sudden you're going to lose connectivity with the server. Typically, you can tweak and configure the ICA protocol to keep the session alive for an extended period of time. But what session reliability will do is it will try to allow you to continue to interact with that session. So it kind of builds a buffer of everything you're typing, every mouse click that you're moving. It builds a buffer so you don't notice that you've lost connectivity. And once you get outside of the tunnel and connectivity is established, the session reliability will flush all that data over to the server. And from your perspective, it should be a seamless transition. Now, in some instances, session reliability will freeze the session because it's lost connectivity. And once connectivity is established again, it gives you access to it. So there's a lot of pros and cons to session reliability. I personally like to use it. I see a lot of benefit in it. If you're going to use session reliability, then you want to make sure port 2598 is open, especially if you're connecting from the outside. TCP port 2512 is for IMA communication, server-to-server communication. TCP 2513 is when you're using your administrative console to communicate with the different XenApp servers. You do that over port 2513. UDP 1604 is for TCP browsing, and I'm just gonna, you have the rest of the ports here. The important ones to know, especially if you're gonna take the exam, 27,000 is the license port, 8082 is the license management console port that you need to connect to your license server. 8082 is by default. Again, 2512, 2513, those might come up on the exam. 2598, 1494, 1604. Those are all good ports to know and memorize, especially if you're taking the exam. All right, now we talked about the XenApp 6 architectural components, but I also wanted to mention the XenApp 6 additional components. And I'm mentioning these components here, first because I want you to know about them, but second because if you're taking the CCA exam, you might be asked about the XenApp 6 components. Don't mix that with the architectural components that I put up in the earlier slide to show you how things interconnect. So the additional components have to do with load manager. That's another component that obviously, as its name implies, will handle load, and you'll be able to figure out, if you have 10 servers in the farm, load manager will help you send the right user to the least busy server, so on and so forth. Resource manager is built on edge side and allows you to track, what the CPU is how much CPU is being used, how much memory is being used, disk, what service is failing. So it's a monitoring and resource management application. It allows you to generate a lot of reports, and it's all built off of the edge side technology. Access gateway, we talked about, the necessity to be able to bridge the gap between users connecting from the outside to the inside. They use the access gateway. The VPX is a virtual appliance. The MPX is a hardware appliance. These are typically, they could be netscalers or they cannot be netscalers. So there's different flavors of the access gateway. There's also a software version, which is a free version, called the Secure Access Gateway. That's still available. Citrix isn't developing it, but it's still available today, so you can use that. But for the most part, the access gateway comes in VPX, MPX /Netscaler. So there's an access gateway and a netscaler. It gets a little confusing, but as long as you know there's an access gateway that runs independent and an access gateway that runs on the netscaler. XenApp Provider, think of the XenApp Provider as another type of monitoring plugin that allows you to plug into things like Microsoft Management Operations Manager, MOM, for example. So it provides you these plugins to plug into these third-party tools which allow you to manage or monitor XenApp 6. The Delivery Services Console, or DSC, is the management console that you use to manage your farm, manage your servers, so it's important to know that. The License Administration Console is, as the name implies, the management console for managing your licenses. And then you have the different Citrix plugins, which we are going to talk about here. So the power of Citrix is that it has a plugin, a client, for almost everything. We can have a client for Windows, for Mac, for Linux, for Java. Anything you can think of, any device, typically iOS, Android, so on and so forth, there is always a Citrix client for that. For the most part, the Citrix clients that you should be aware of are the XenApp plugin for hosted applications. That's typically the XenApp plugin that you would use if you're trying to launch published applications. You have another plugin for your streamed applications that you run on your endpoint. There's a web plugin. It's a smaller version of the online plugin that it's a smaller footprint, so you install that off of the web. There's a client version for Java, and then there's the Citrix receiver that is sort of the next generation Citrix client where everything is going to a Citrix receiver. Most of the mobile devices, or all of the mobile devices today, have a Citrix receiver, and therefore I think in the near future we're going to see a consolidation of all of these plugins into just Citrix receiver. And finally, let's go back and recap what we've learned during this lesson. So we started off by talking about independent computing architecture, the ICA protocol, and why it's so important to any Citrix product. It is the flagship feature that makes Citrix so flexible, so thin, so easy to use, and so performance friendly. So it works good on the LAN and the WAN. It works great remotely. It works over standard SSL, so you don't need to change or tweak it. So the independent computing architecture is a very thin protocol, latency sensitive, you can tweak the bandwidth on it. So if you're sending printing jobs through the ICA protocol, you can tweak how much bandwidth that particular print job can consume if it's part of the ICA protocol. Now keep in mind, you can send printing as part of the ICA protocol as a virtual channel, and I'm going to show you as we start talking and getting into more advanced lessons how you can take printing outside of the ICA protocol and thereby even enhancing the speed and reliability of the ICA packet, because you're taking that virtual channel, the printing virtual channel, outside of it, and thereby you're making that packet even thinner. We talked about the ICA packet. We talked about the different components of the ICA packet and how the command frame is the only required piece of data that's available in the ICA packet. We talked about the other components that make up the ICA packet, which are all of them are optional, like the frame head, the frame trail, the reliability, the compression, the encryption, the command data. We talked about the different virtual channels that are available within the ICA packet, and there are up to 32 virtual channels. We also mentioned that the ICA protocol virtual channels are different than the RDP virtual channels. We talked about the Independent Management Architecture, or IMA, and how that's a framework for server-to-server communication and for you to be able to issue commands from your management console to your XenApp servers. We talked about the different XenApp architectural components, and we showed you a graph of how these components are tied together and what their functions are. We talked about zones and how you can use zones to geographically group XenApp servers that are in one location so that you minimize the amount of IMA communication and confine it to that particular zone, because typically an IMA is going to try to communicate with all the XenApp servers that are available. So if you have a zone that's geographically spread, then IMA is going to be talking all over the place. So you want to limit that level of communication to the XenApp servers in one location, which will streamline and make the communication and the performance more efficient. So that's why you create zones based on geographical locations. We then moved on and talked about the different ports that are required in your XenApp environment. We talked about 1494 as being the ICA protocol, 2598 ICA and session reliability, 2512 server-to-server communication, 2513 management console to server communication, so on and so forth. All of these are important ports to know for your day-to-day administration troubleshooting, but also for your XenApp or your CCA exam. We talked about the different components, and we also talked about the different XenApp plugins. From a component standpoint, we talked about the load manager, resource manager built on EdgeSite, and we went through the whole list. We also talked about the XenApp plugins, how you have a plugin for hosted applications, for streamed applications, you have one for Java, and you have the Citrix receiver, which is the new generation of Citrix clients, and you already have one for all the different mobile devices, iPads, tablets, phones, so on and so forth, but you also have it for Windows, for Mac, for Linux, and for Java. So I hope this was a very informative architectural session that gave you insight into the ins and outs, into the plumbing of XenApp, and I hope this was a good building block that we can build on moving forward in the course so that you know how things are tied together. I hope this was informative for you, and I'd like to thank you for viewing.